Today, it's assumed that a game will run on many different kinds of hardware. Players expect the game to be aesthetically pleasing and to play smoothly across a broad range of specs, including low end devices. With Unity's universal render pipeline, you can achieve great looking graphics using artist friendly workflows that let you quickly create optimized graphics for different platforms from mobile to high end consoles and PCs. The key is in the many optimizations performed behind the scenes, crunching every factor that goes into a perfect frame. My name is Arvind Neelakantan, and I'm the head of technology for Unity India. In this talk, I'll discuss those factors, introduce some real time concepts, and walk you through common lighting configurations in Unity to help bridge the gap between aesthetics and performance using an in house game demo to see the effects at work. By the end, you'll come away with concrete advice and valuable lighting tips that you can bring to your own projects. I'll begin by showing you how you can get started with the Unity editor and Universal Render pipeline. Then I'll show you how to lay the foundation of lighting your scene using real-time directional lighting. I will follow that by how you can create realistic bounced lighting using global illumination, how you can create a sense of connectedness among objects in the game using reflections, and finally, how you can dramatically improve your scene without altering your existing content using post processing. Throughout this talk, I'll be drawing practical examples from the boat attack sample game. Boat Attack is a real world boat racing game that plays beautifully across platforms including desktop, mobile and consoles. Now this demo was developed in-house by the Unity R&D team to drive product development and to showcase the features and benefits of the Universal Render pipeline. You can download the demo from the link provided in the description below. Let's get started. The first thing to know before you can think about lighting for your project is that you need to select your scriptable render pipeline. Each of the available pipelines have different strengths, and choosing the best one for the job depends on your goals and circumstances. Since the goal of this talk is to help you achieve high fidelity lighting with maximum performance and platform reach, the optimal pipeline to work in is Unity's Universal Render Pipeline or URP. I have already opened the Boat Attack project in my editor, and as you can see from my package manager window, Universal Render Pipeline or URP is already installed in this project. The goal of URP is to provide optimized real-time rendering on a wide selection of high to lower power devices, which is achieved by constraining options and guiding users towards performant rendering choices with regard to lighting and shading. Let's get into lighting. In lighting, the process starts with real-time directional lighting, which lays the foundation when you begin lighting your scene. To keep performance in mind, URP has what is called direct lights, which only have a limited subset of features. The number of lights in your scene are controlled from the URP asset. In Boat Attack, you can access the URP asset by going to Edit, Project Settings, Graphics, and selecting the URP asset that has been added over here. By selecting the URP asset, you can go under the lighting settings where you can notice that URP has one main light, also known as the directional light, and additional lights which are local lights with a limited count that supplement the main light. Now, as additional information, if you're used to the built-in render pipeline, then local lights are the equivalent of pixel lights that you see over there. With the main light and local light set up, you can now get your hands dirty with actually lighting your scene. In Boat Attack, we are not really using any local lights and we are only using one main light that you can see in the hierarchy. The main light is useful for creating effects such as the sunlight in your scene. And the most important thing to note with directional light is that objects are illuminated based on the direction of the light. And that means the distance of where the light is really doesn't matter. It's only the direction or the rotation that affects your main light. With that set up, we will now start seeing shadows in the scene. Now, shadows can be quite expensive and are far from free. Now, any game object like the rock that you're seeing here that can cast a shadow must first be rendered into what is called a shadow map. then that map will be used to render objects that might receive shadows. For directional light, the shadow map covers a large portion of the scene, which can lead to a problem called perspective aliasing. Now, perspective aliasing means that the shadow map pixels close to the camera look enlarged and chunky compared to those farther away. URP solves this using cascaded shadow maps. Cascaded shadow maps break the camera's frustum depth into regions that can be covered with shadow maps proportional to the screen estate that they occupy. Let me show you how that works. You can configure shadow cascades in the Universal Render Pipeline asset. The more cascades you use, the less your shadows are affected by perspective aliasing problem. You can increase the number of cascades, but you should keep in mind that increasing the number increases the rendering overhead. However, this overhead is still less than what it would be if you were to use the high resolution map across the whole shadow. Importantly, only the main light lets you have cascade shadows. All other directional lights are non-shadowed and will be classified as the additional light that you saw earlier. As you can see, real-time lights are expensive and there are a lot of constraints around how you can use them. Because of this, effects such as light scattering or calculating bounced light are prohibitively expensive to use in real time. Now that doesn't mean you cannot achieve them. Unity uses a process called baked global illumination that makes realistic bounce lighting feasible in game by calculating the light transport offline and storing the results using a number of techniques such as the use of light maps, light probes, and reflection probes. Let me show you how that's done. Let's begin with light maps. Light maps are essentially textures that store lighting. Be it direct lighting, indirect lighting, or shadow maps, all of them can be encoded into light maps. Now you need to make sure that objects are set to contribute to GI by selecting an object, going under static, and ensuring that contribute GI is checked. And only those objects are considered during light map baking. You can bake light maps by going to the lighting settings window. You can access the lighting settings window by going to Window, Rendering, Lighting Settings. This will open up the lighting settings window. In Board Attack, you can see that the Baked Global Illumination checkbox is already checked and the lighting mode is set to Baked Indirect. Now this setting bakes the directional light to create real-time lighting along with the high-fidelity directional lighting, which is especially useful since this option allows us to move the directional light around without fixing its direction during the game development process. Now the rest of the options define the resolution and fidelity of the light map. You can configure how many lighting samples you need to retrieve lighting information from. You can also optimize the sample counts to achieve noiseless bakes in a reasonable amount of time. Denoise to clean up lower sample bakes, for example. And once they are set up, you can just click on the generate lighting button. As you can see in this game, I've already baked the light map and you can visualize the bake in a couple of ways. You can select the baked light maps tab that you can see in the lighting window and you can select the baked light map and you can even open it up in your favorite image editing tool like Photoshop here, for example, or you can also visualize them in editor by selecting the baked light map option that you can see in the scene window. So if you go to shaded, that will show the entire view as it is baked. And if you select baked light map, that will only show you the scene with the baked light map textures. Now in Unity, light mapping is an integral part of the rendering engine that directly affects the quality of lighting in any given scene, from the smoothness of the shadows to the blending between light and dark areas. As mentioned earlier, only static objects are considered by Unity's baked GI systems. But what about dynamic objects like the boat? How do they pick up some of the rich bounce light that the static geometry receives? In order to do that, the lighting information must be recorded in a format that can be quickly read and be used in lighting equations during the gameplay itself. After establishing the ambient lighting and light mapping settings, you can use Light Probe Group to illuminate the remaining props and dynamic objects. Now you can create a new Light Probe Group by going to Game Object, Light, and Light Probe Group. Now in Board Attack, we use only one Light Probe group that pretty much sprawls the entire scene. Now this scene here uses an array of probes in the path that the boat is going to be taking, which is pretty much just on the water. Now you need to ensure that None of these probes don't end up inside a game object though. If you have seen any computer generated films or played high end console games, they commonly feature highly realistic reflections. Reflections are important because they create a sense of connectedness among the objects in the game. However, the accuracy of these reflections comes at a very high cost in processor time. This isn't a problem for high end devices, but it is severely limited in lower end devices. So, how do we have great looking reflections but also have it work on low end devices? Enter reflection probes, or more specifically, baked reflection probes. You can create reflection probes by going to Game Object, Light, Reflection Probe. Now, for an object to show these reflections, its shader must have access to the images representing the cube map. Now, you can set this up by selecting an object, for example, this rock, and under static, ensure that reflection probe static is turned on. Now, each point of the object surface can see a small area of the cube map in the direction that the surface faces, that is, the direction of the surface normal. Now in boat attack, we have set up a number of static reflection probes, each local to different areas. So if I select the RP cave entrance, that is specific to the entrance of the cave, as you can see right here, or if we go to the cave exit point, that is specific to the exit of the cave itself. Now using more localized reflection probes ensure that you have a greater precision in the indirect reflections because they provide more accurate reflections in the less open areas. By selecting the reflection probe and having it marked as baked, you can see all of the objects that are marked as reflection probe static are now baked into this reflection probe map. Now, reflection probes are kept to a minimum since these are loaded with the scene, and therefore there is a risk of increasing the loading time of your game at the beginning of your game start. Finally, we come to post processing. Post processing is a set of rendering effects that you apply based on your existing rendered scene before generating the final render. This means you get instant visual feedback for the effects that you choose. In URP, many rendering and post processing properties are driven by a volume framework. Your settings will essentially be organized in categories attached to the volume component. You can create a new volume by right clicking in the hierarchy, going under volumes and selecting the many volume type options that is available. Or you can also select any game object that's there in your hierarchy and click on the add component button in the inspector and add the volume component to it. This approach means that individual volumes can be given priority and weighting that determine how attached properties blend with each other as the boat travels, say, between darker caves and the open sky. Now, working with volumes at different scales, such as globally or locally or even per shot, provides fine grained controls over rendering for a variety of contexts. Now, this workflow means that volumes, which are typically stored in as a separate asset, are perfect for experimentation since you can duplicate a volume profile, for example, and play around with its configuration, then revert back to its original volume with very little consequence. Now, post processing effects can take up a lot of frame time. So, if you're using URP for mobile devices, you need to ensure that you have the most mobile friendly post processing effects that you can use. As you can see in my boat attack game, I've added the volume component to my island level game object. Now, certain post processing effects like bloom with high quality filtering disabled, chromatic aberration, color grading, lens distortion, and vignette are some of the more friendlier for lower end devices post processing effects. And you can add them by going to add override, post processing, and selecting the post processing effects that you can see right here. Now you can play around with them to achieve the best look that you need for this game, and details about all the post-processing effects are actually added to the Boat Attack ebook that is given in the description below. So in this talk, I have covered some best practices that a game artist or even a game developer should follow to get the most out of Unity's universal render pipeline for great looking lighting. So to conclude, URP aims to be the future default render pipeline for Unity. It's more flexible, more extensible, and delivers higher performance than the built-in render pipeline with improved graphic quality. Direct lights have a limited subset of features to keep them performance oriented, and ensure that the ability to target as many platforms as possible is available through it. Also, in order to achieve great looking lighting, it involves light bounces and light scattering while also having results with playable frame rates. Now, Unity must perform all of these calculations during edit time and encode the results in a way that can be quickly read during gameplay, and this is what we call as baking. And finally, baked reflection probes and post processing effects to your game can be added to your game to create a sense of connectedness and full screen effects that can greatly improve the appearance of your application or your game with very little setup time. So, with that, you can download the ebook on lighting up your graphics, which goes in depth into each of these concepts that I just explained. You can download the boat attack demo to explore how lighting was set up for that game particularly. Now, Unity is more accessible than ever to creators and technical directors. So, take the Unity Learn free 1 hour tutorial, which introduces lighting and rendering to get you more comfortable with how lighting works in Unity. And you can also watch a lot more webinars and sessions from our resources link. So, thank you and have a great day.